Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to provide a couple examples of how to handle problems about relative velocity. Okay, so we're going to talk about John and Tim here. And John is the one in the boat, and Timmy here is on the other side of this river, which is a 1/4 mile wide. And John wants to visit his friend, Timmy. Now John, he can row that boat 3 miles per hour in still water. The river itself, however, is moving 2 miles per hour to the right. So the question we're going to work on is how far downstream will John end up if he tries to row directly as shown, meaning that he keeps the boat pointed directly like this. So this velocity vector that I'm drawing, that's going to be the velocity of the boat, and that's going to be with respect to the water. But as the water moves downstream, right, that's going to carry the water and the boat with it. So there's a vector for the velocity of the water, let's say with respect to the land. And the boat's actually going to move in a direction something like this. So that's going to be the velocity of the boat with respect to the land. And there's some sort of angle here that we're going to calculate. Now, the river here is moving at 2 miles per hour, and John can row that boat at 3 miles per hour. And the trig function that relates those is the tangent function. So I'm going to go ahead and write out the tangent of the angle theta is equal to, right, adjacent divided by, opposite divided by adjacent. So that's going to be 2/3. And we can go ahead and calculate theta. Theta is going to be the inverse tangent then of 2/3. And if you give me a moment here, I haven't worked that out yet. Inverse tangent of 2/3. Oh, and I get a number here, and it's given it to me in radians. Give me a moment. So I get about 33.7 degrees. Now, to actually answer the question, it says something like, how far downstream does he end up? All right, so I'm going to draw another picture. But that's all about distances. So I'm going to draw another triangle here. And that distance right there, that's what it's asking for, how far downstream John actually ends up. Now, that's a different triangle than this one. This one was the triangle about the velocity vectors, but that angle is the same. This triangle has all the same trig ratios. So let's see, this side is opposite theta, so let's go ahead and write this out. The tangent of the angle theta is going to be the side opposite, that's what we're looking for, d divided by the side adjacent, and this distance here is the 0.25 miles. So d is going to be 0.25 miles times the tangent of 33.7 degrees. By the way, you can just use 2/3 if you wish for that. I get 0.17 miles. And we can convert that to feet by multiplying by 5,280. It doesn't actually say to do that, but all right, so that gives us a distance of approximately 880 feet. So John's going to have quite a little ways to hike back to his buddy Tim there to meet up. All right, next problem. If John were to do that. But instead, John decides to cheat the river somewhat by pointing the boat upstream here. All right, so the velocity vector for the boat with respect to the water would look something like this. And this angle theta here is what we're going to find. And again, the river now, the velocity vector for the river points this way, so that's the velocity, let's say, of the water with respect to the land. And the boat's net velocity, this is what John wants, is to be this way. So that's going to be the velocity of the boat now with respect to the land. If John wants to end up over here, his net velocity vector needs to point in that direction. Okay, so remember, John can row that boat at 3 miles per hour. The river is moving at 2 miles per hour. And the trig function now that relates these is the sine function, because this is opposite and this is now the hypotenuse. So let's go ahead and write out that the sine of the angle theta is equal to 2/3, and we can solve that for theta easy enough. Give me a moment. I got about 41.8 degrees. Let's say about 42 degrees. So he's going to need to cheat that river fairly considerably on that angle to end up going directly across. And let's see, also, how long will it take? All right, so the how long part, that's basically a speed is distance over time question. There's no accelerations in this to worry about. I'm not going to worry about graphs. The thing that's important to realize is that what speed are we going to use? This is actually the net velocity, not this one. Timmy's no longer, or John's not going to move at 3 miles per hour. He's going to move at some speed slower than that. So we're going to start by calculating that. And there's a couple of ways we could calculate it. We could use either trig functions or by Pythagorean theorem. I'm going to go ahead and just use trig functions here. So the cosine of 42 degrees is going to equal the side adjacent divided by the hypotenuse. So that's going to be velocity of the boat with respect to the land divided by the 3 miles per hour. So the velocity of the boat with respect to the land, again, that was a B. Give me a moment here. Oops. Got this new calculator I'm trying to figure out how to use here. Darn it. Okay, I had to kind of do a long about way there, but I get I get 1.13 mile per hour. I'm getting used to a new calculator here. I downloaded on my phone, so I'll put a little qualifier against that. This is how fast that boat is going to make progress moving in this direction. So we're going to use that for the speed here, 1.13 mile per hour. The distance is 0.25 miles over time. If we solve that for t, I get a time of 0.22 hours, which is about 13 minutes, 13.3 minutes, approximately 13.3 minutes. Okay, so there you have it, folks. I just wanted to make this as kind of an introductory video here of providing examples how to handle relative velocities. I hope that this has done that for you. Have a great day.